Today we're going to look at exponential functions, and you can use the date of June 3rd. Your note packet has 5 pages. These are the first 3 and the last 2. And you won't need a ruler. We're going to sketch smooth curves today. If you're going to work with an exponential function, you're going to see a general format like we have here, y equals a times b to the x power. If you have an exponential function, you're going to have a variable in the place of a numerical exponent. So we have x as our exponent instead of 2 or 3 or 10. When an exponential function is graphed, it has a very basic shape that's easy to recognize. This is the basic shape for an exponential function that is growing. We can modify our parent function. So the value of a is going to represent an initial amount that you start with. If you're going to invest money in the stock market, maybe you decide to start with $100. The value of a would then be 100. Maybe you're going to stock a brand new pond. So you're going to throw in 20 fish. So a is 20, the initial amount of fish that you start with. The value of b is going to be our growth factor, and I have growth in quotes because sometimes it's actually a decay factor, and the graph will look a little different in that case. Our growth factor b does have to be greater than 0, or else you won't see growth, and in some cases you won't see anything but a straight line. And b cannot be 1, and we'll talk more about that in a minute. Your exponent, x, can take the form of any real number. So it can be a positive number, negative, it can be a fraction, a decimal. It just cannot be anything irrational. Some basic facts about the parent function. So if you have a parent function, your graph will always contain the point 0, 1. And you can see that on both of these, although only the green is the parent function. The growth factor can be anything as long as it's greater than 1, but the power itself needs to be greater than 0 to show any kind of growth. If b is greater than 1, and 2 is the normal parent function, but it can be 3 or 10, as you read the graph from left to right, you should see an increase. And eventually, if we follow the path of this green function, it should start to grow rapidly and go up very quickly. If b happens to be between 0 and 1, what we have then is a graph that is decaying. So you can see here with the red graph, the base b is 1/2, and it actually decays really quickly, and then it starts to level off, and it almost looks like it appears to become a straight line. If you have 2 identical bases, so the value of b, your growth factor, is the same, then you can simply set the exponents equal to each other and then solve them if they are an equation. We have a few restrictions on b, our growth or decay factor. We can't use the values of 1 or 0. They will give you a constant function. That means we'll get some kind of straight line function, which is not exponential growth or decay. So as an example, if you used 0 as your growth factor, 0 raised to any power is going to give you 0. This is really the equation y equals 0, which is the x-axis. That's horizontal, and it's not growing, it's not decaying, it's just remaining constant. The same thing happens when you use 1 as a base. 1 to any power, regardless of what x is, will always be 1. So your equation is really y equals 1. And again, that's a constant function that's not growing or decaying. What you'll notice with all exponential functions, besides the fact they have the same shape, is that they appear to approach a certain value, but then don't ever get there. So this is what we call an asymptote. This is a line that the graph will approach, but will never get there. So in this picture, Even though this is growth, this end here on the left is approaching the asymptote. If you have a basic exponential function in this format, it's going to have a horizontal asymptote. In this particular case, the asymptote is at y equals 0. But as we modify the function, the asymptote will move its place away from y equals 0, but it will remain horizontal. We spoke of end behavior in our last lesson. The end behavior for exponential functions is always very predictable. One end is going to approach the asymptote. So in this picture here, the left-hand side is approaching the asymptote. The other end will approach infinity. So my right-hand side is just going up, and the arrow says it goes up forever, so it's approaching positive infinity. Because this is a smooth curve that grows very slowly at first and then increases at the end rapidly, we can calculate average rate of change, and I'm abbreviating that as AROC. This is technically just the slope formula, but we're not calculating slope specifically because that would refer to a constant rate of change. And with exponential growth or decay, the rate of change is not constant between any two set of points. So let's try to graph our first example. On your iPad, you want to put in 5 times 2 to the x power. Remember, 5 is our initial value, and the growth rate is 2. So your graph should look like this. We can see 5 here is our initial value. If we generate the table from the iPad, you can graph as many points as possible. Obviously, some of these are too big to graph. But you'll also notice in the table that around -3 and -4, we're starting to decline. We're never quite getting to 0 though, but it's approaching 0. And you can see it in the graph. So our asymptote will be this line right here. And the equation is y equals 0. So the graph will never really touch 0, although the graph might look like it. On the iPad, the table will eventually convert these answers to 0, but it's not really there. In example number 2, our growth rate is actually decay. We're using a base of 1/2. So let's put this into our iPad and graph it first. And this is the shape of decay. It's falling quickly and then leveling off. You'll notice that we've modified. It's not just 1/2 to the x power. We also have +1. If I look at my table, again, you can graph as many of these as possible. And we start to get into some decimal values at 1. But if you notice in the table, we're approaching 1, and the decimal part itself is getting very small, but we're not really ever going to get to 1. So that tells me that's where the asymptote is. You can also see it in the graph. It's leveling off here. And you can almost imagine a straight line here at y equals 1. So that is the asymptote. And the equation is y equals 1. Remember, all horizontal lines start with y equal, and then it refers to their intercept. In example 3, we've done quite a bit to the original function. We're going to go ahead and graph that on the iPad. And when I look at my table again, I have some whole values that I can graph. And when you look at the table, it appears as though it's approaching -2. I see that in my function. It's never going to quite get to -2. So as we're growing here, this side, the left-hand side, is showing me where the asymptote is also lying. And the equation will be y equals -2. This is your homework for tonight. This is number 125. We're going to sketch graphs and include tables of each of the functions, and then you're going to write the equation for the asymptote. If you have any questions with this assignment, please contact me, and I'm happy to help. Have a great day.